Welcome everybody to part 2 of the rise and stall of the piston engine. In this part, we're going to look at the extreme heat loss that is generated by just about every engine out there on the road. Okay, so we're going to look at the modern piston engine with all of its components. The way they fit all this together is, it's a work of art. I don't deny that. And I used to love this kind of machinery. In fact, I still do for certain things. But you have to keep in mind that that engine is absolutely worthless unless it has this to go with it, the radiator, and has an exhaust system to dump all of this heat out of the engine. And that is the issue we're going to take up with part 2. Okay, so the petroleum piston engine, heat losses. That's the problem with it. And we get heat losses, obviously, from the radiator and fan. We get the heat that's lost out of the exhaust pipe. We get the heat that's lost out of any oil coolers or transmission coolers. We get the heat that's lost out of the air conditioner. That's right. We lose heat out of the air conditioner because we have to burn more fuel to power it. Last is the heat of friction of the engine itself, the pistons rubbing on each other, the camshafts rubbing on the lifters, etc. These are all major red flags. If we were looking at this from an efficiency standpoint, we have all these heat losses. Each one of these is a red flag. Heat loss means energy loss. And where do we see this going on? In the oil industry. They get away with losing this heat all the time. Why is that? Well, they supply energy. So who are they really in competition with? Anytime you're designing a mechanical device, if there's an energy loss, it means there's a bad design. The same way with an electrical circuit. Let's look at some designs that we've had. I'll just randomly look at 1960s Cadillac and Lincoln. And I pulled this out of the archives. It's showing that fuel consumption of a 1965 Cadillac Coupe de Ville was 11.2 miles per gallon. That sounds pretty bad. Well, I guess the 1950s Cadillac was probably even worse, huh? How did it come out? 13.3. Interesting. It's actually, it looks like 11.1 on U.S. gallons. That makes me, the Cadillac was only on U.S. gallons. It was only at 9.3. Well, that's kind of odd that a vehicle that was 5 years or 10 years older was getting better fuel mileage. Well, let's move on. Let's go back even further to 1927 before they had a Lincoln. We'll look at the 1927 Pierce Arrow. According to their sales brochure, it's getting 14 to 17 miles per gallon. Might add it had an 18-gallon tank, so that would be in line with these other vehicles that we looked at. They had around 18 to 20 so gallon tanks, indicating that they're getting about the same fuel mileage. Let's take a look at a 2018 Cadillac Escalade, and we're at 16 miles per gallon. This is what it's actually getting. I don't care what's posted on the window. This is from Fuelie.com, and these are actually registered car owners. They're operating them, recording their mileage with a fill-up, only a fill-up, and a mileage recording, and that's the actual mileage that they're getting today, 16. So, folks, how are they getting away with this? I mean, we've got all this technology, but do you see what's going on here? And the biggest red flag of all is the fact we're still using gasoline. And it's toxic, and it burns poorly. And it's the only fuel that produces carbon monoxide, which is deathly poisonous to humans when they breathe it. It is prone to detonation, so you have to run it in a low compression engine. And when you run low compression, that's going to hurt your fuel economy. So, there's just a huge number of red flags with this engine. And the fact that we're using the toxic gasoline still, this is what the industry has been allowed to leave behind, are abandoned fuel stations that nobody wants to move back onto because they've got leaky tanks on the property. And they've been allowed to just walk away from these things. It's unbelievable. I mean, how do they ever get away with this? This is what becomes of these old stations that are been handling this toxic fuel. I mean, it is a real nightmare to clean up. Nobody can afford to do so. Continued problems with this heat loss. Now, here is shown an engine on a test stand that's being run at pretty much full load. And you can see how hot the thing's going to get. And so not only are you losing heat out the exhaust of the turbocharger here, you're losing all this heat off of the, it's radiating off of the metal. And this is an important part of keeping the engine cool. The engine itself needs to radiate heat. And this is a violation of the conservation of energy, which is defined in the first law of thermodynamics. And this has been going on since the invention of the piston engine. Well, actually, they had this problem solved. This is 1872, the Brayton two-cycle engine. And I've got lots of these. I just happened to grab this one because I had only recently run across. But you can look as early as 1872, how smart we were then. We're already using a simple method. So it's 1872. Your name is Brayton. You've designed this simple piston engine that goes up and down, and the top piston is going to pressurize. You're just going to use that as an air pump. It's going to pressurize your fuel in this reserve tank, and then it's going to feed the fuel under pressure and heat into the combustion area. In 1872, they'd already figured out how to heat the fuel and pressurize the fuel because that was going to atomize it and burn it so much more efficiently. And they'd already come up with a piston engine that was 10 times simpler than what we ended up with. By the way, this is a flywheel. It's turning, and you don't exactly see the crankshaft, but any piston motion is up and down, and it is easy to transform that into rotational motion. This particular engine was only a two-stroke engine, not a four-stroke, which means it produced power on every revolution, every stroke. And the Brayton engine also used a separate compressor. I mentioned that. And then they were basically a vapor engine that utilized the heat to preheat the fuel going in the engine. But people were smart back in those days. And this is just an example of many that have been discarded. So we look at the standard petroleum engine, and in a rough analysis, it breaks down like this. A third of the fuel burned is going to be used to push the vehicle. A third of the fuel burned is going to be needed just to make this engine run itself, compress all that air and gas at 4,000 RPM or whatever. And a third of the fuel that's burned is lost as heat to the environment. Okay, that's your radiator, your exhaust pipes, the oil coolers, etc. That's a third of the fuel. And so we end up with very little of the fuel is actually being used to push the vehicle. So how is it possible to get good fuel mileage out of this engine? It's very difficult, and the oil industry likes that just fine. Well, let's take a look at one major red flag that they're not tapping into. This is a picture, a diagram, of your standard recreational vehicle refrigerator. Standard recreational vehicle refrigerator runs off kerosene or natural gas. You see, it's coming in here. It's using fire to cool. Well, you can either compress a gas, which makes it warm, and then you can let it cool and expand it to make it much cooler, so you have the refrigeration. Or you can pressurize it by using fire. Then cool it down at that pressure, and then expand it. And you've knocked the temperature down again in the expander. And that's how a refrigeration cycle that uses energy and creates heat by burning that energy, that's how it actually powers a refrigeration cycle. Now, this is what it looks like. It doesn't even require a pump. It uses gravity. And these are in virtually every recreational vehicle that's out there. Could easily be using the exhaust pipe. You see, here's the chimney. This could be the exhaust manifold of your engine. We could easily run an air conditioning system off of our exhaust heat. We don't do it. And, we're not that stupid. You can go back hundreds of years where they're just designing chimneys. They're doing everything they can here to hold the heat in. And so your fire is down here, 1,500 degrees. By the time it gets up here, you want most of that heat to have been absorbed in here. We've been trying to capture the heat from day one. Let's look at a bread oven, the way it's designed. The fire's down here. The heat comes up and it goes all over, and it has to, in order for the heat to escape, it has to go through this thick wall of stone and mud. And so it's designed to trap all the heat in, so that by the time the heat's going out the top, It's only at maybe 400 degrees, not 1,500 degrees down here where you started. And so here we are with our modern engines. Who cares? We just dump it all. We just dump it straight out the exhaust pipe and into the radiators, etc. And so here we are in 2018. A third of the fuel that we're burning is running the engine. That's much bigger than it needs to be. I discussed that in the last session, where if we used a better fuel, we could design our engines about 1/4 the size, and that will only take 1/4 of the fuel to run the engine. That's right. That's why it's beneficial to use a smaller engine. And a third of the fuel burned is lost to the environment. This is 2018. We're still just dumping a third of the fuel we burned, which is toxic gasoline. We're still just dumping that extra heat into the environment. Let's face it. The oil industry designed the best petroleum-consuming device they could have ever come up with. And this is a big win. This is a win for big oiling. Let's review. 1964, Chrysler turbine. Look at all these turbine engines around here. This is the latest one up here. This is some of the earlier ones. And we look at the Chrysler turbine. It used a regenerative exhaust gas system. If you notice that the exhaust gas went through a regenerator, that heated the incoming air. So what happened is 1,375 degree air became 525 degree air. And the Chrysler turbine had the lowest exhaust temperatures out the tailpipe. It had the lowest exhaust temperatures of any car out there. So guess what? We didn't get to have it because we were capturing the heat. It was capturing the heat of the exhaust. And we didn't even get a simple rotary engine. This is a small Wankel engines you can that are being fitted into unmanned aerial vehicles. Yes, there's a huge market for Wankel engines out there. They're being manufactured in greater numbers than ever before, even though that Mazda canceled the design, or 2007, somewhere around there. But these engines are great. They don't produce that much heat because there's not nearly as much friction. There's hardly any friction at all. Now, this does have a liquid cooling radiator attached to it. It's not shown. I don't want to totally mislead you. But these engines generate much less heat, and they are much more efficient. That's why they're using in unmanned aerial vehicles, because they are efficient. We got a little shortchanged on the Wankel design. So let's sum it up. Some of the piston engine deficiencies. We've got the radiator and fan, the exhaust pipe, oil and transmission coolers, air conditioners, and we got excessive friction from the engine. We're also add on that we've got poor fuel, and we've got non-regenerative brakes. We're still using brake pads, even though we've known how to use an electronic brake that would give us power back since the invention of the electric motor itself. And we've still got rubber tires on soft asphalt, and we've got poor aerodynamics. And I just want to make a little plug for a steam injection device for internal combustion engine. This was invented July 10th, 1970. It's just one of many inventions out there. It says a steam generating tube is mounted in the exhaust manifold of the engine and supplied with water from a water tank. Steam generated in the tube passes through a steam separator, and substantially dry steam is injected into the intake manifold of the engine to pass into the cylinders along with the fuel and air mixture from the carburetor. And what does this do? It gives you more compression, eliminates smog, and gives you better fuel mileage. Did we ever see it? Heck no. The gasoline piston engine officially invented in 1885. Actually, you saw that in 1872 they had a superior one with a Brayton engine. It's remained in service now for 133 years. What can we do about this? Well, we can stop buying their stupid designs, and that's as easy as just hanging on to your existing cars for a few extra years. That is all the time it'll take to bring them to their knees. The other thing we can start doing is we can start laughing at the car salesman. Oh yeah, it's time these car salesmen started to wake up too. Because anything, what is a stupid design? A stupid design is anything with a piston engine that runs on a toxic fuel. Let's start getting that word out from the bottom up. It's bound to reach the top. When somebody who's selling BMWs and Porsches and things like that is being told, hey, you've got a stupid design running on a toxic fuel. They'll say, well, give me a better design. Well, how about a turbine? How about a Wankel? How about an electric car? How about the fuel cell that went up with Apollo that all it needs is a wheel hub motor? See what they say then. Maybe they'll pass this up the line, and people walking out of their showroom saying, hey, I don't want this junk, because that's exactly what we ought to be saying. And now that you've seen this, you're a lot more prepared to go in and make a deal on a Porsche or a BMW. Be a lot more realistic discussion. And I might add that we don't want some downsized, scrumped up ride. It's time to get the same level of safety as the person driving an 18-wheel truck alongside of us. Look, if they can't make our cars smash-proof next to those trucks, then put those trucks on a separate highway. But I think they can make us smash-proof during the interim, and if it takes quarter-inch special molded aluminum, mixed with carbon or carbon fiber, they have the material. I've already, it uses magnesium and aluminum mixed together. They have it. They can make something that's lighter than aluminum, that's stronger than steel, and that's what we need in the way of a car body. Do we deserve it? Yes, we deserve it. Every human being is entitled to a certain level of security. We have the right to demand a transportation system that does not expose a person to any unnecessary risk. And let's face it, the way it is right now, we put our family in a car and we drive across the city, and we're lucky that we don't have an accident. I mean, if one person just has a short lapse of concentration and goes out of their lane, or if a wheel goes bad, a tire blows, or if a truck has something go wrong with its trailer, we're just right there. There's just no buffer. And this is a crazy system. And yes, we deserve a system that we can actually put our family in and drive to a ball game and know for sure we're going to get there without having some kind of tragedy. And also consider that it's a miracle that there are not more fatal accidents than there are. With this system being what it is amazing. It works as good as it does. And I attribute that to drivers. The fact that the human factor out there makes this system work. It's not a good system. The only reason it works is because humans make it work. And I know myself, I've been saved from horrible accidents by a couple of drivers out there who are really alert. And I've also prevented a number myself because I was just watching that person. I thought, well, they just might pull out. They might, and they did. And I was right there, just hit that brake and swerve just right so that no contact. We could be doing so much better from an environmental point of view. We could have a totally non-toxic fuel. We wouldn't have any polluted rivers, lakes, and air. That's what this is all about. It's not to whine. It's to bring the oil industry and the car industry into reality and give us a non-toxic fuel and give us a vehicle that we're protected in. Quit giving us the design that so obviously wastes most of the fuel that is pumped into it. Okay, so thank you for listening and watching. Leave your comments below. Subscribe if you want more. Thank you very much. I'll see you in the next video.